And I'm going to talk about how you can build Flutter SDK using Rust for the core. So some quick disclaimers before we get started. There's going to be a lot of code on the slides, so if you want to see it a bit clearer, come to the front. And there's 10 minutes at the end for questions, but feel free to interrupt halfway through if you can shout. So in this talk, we're going to cover how you can use Rust in your SDK, whether or not you should. It's not always the right choice for every SDK, and then some issues we hit at Ditto when we were building ours. So if you've never come across Rust before, it's a high-performance programming language built by Mozilla originally. It's now open source. It's got speed sort of comparable to C and C++. People will argue about which one's faster. They're about the same. But unlike C and C++, memory safety is a huge focus. It is a memory-safe language. You can break that in ways, but that's true with many memory-safe languages. And it gives you the performance of C with the safety of Python. It's sort of one of their taglines. Originally built by Mozilla, they had a really long-standing CSS rendering bug that prevented them from sort of figuring out CSS rules in parallel, which is something that you'd imagine CSS would be quite good at, but they couldn't do it, and they thought it was easier to build an entirely new programming language to do it. And they were right. The bug got solved with Rust 15 years later. Obviously, Firefox is written in C++, so for Rust to be useful in Firefox, it has to be compatible with C++. You have to be able to call one from the other, and vice versa. Part of that is not having any runtime, or a very, very minimal runtime. So there's no VM, there's no garbage collector, there's nothing like that, because that's overhead to every call, and that's something that's just unacceptable for Firefox. It's not an object-oriented language. There's no classes, there's no inheritance. They do have encapsulation, they do have polymorphism, but it takes a slightly different approach. So if you've never seen any, here's some snippets. First impressions, probably it's quite similar to Dart in a lot of ways. You've got a few differences. You've got the little arrow for the return type and let mut instead of var, but they're quite similar looking languages on the surface. Rust is a very sort of type-driven language, but it's got powerful type inference. So, just like Dart, you don't need to write like int count equals 0 or whatever. You can just let the compiler figure it out. There's a slightly more complex example. Here we've got an enum, which is not like a Dart enum. It's much closer to like a sealed class. It's one of these possible cases, and each of these, it might be a point with no data, a circle which has a single field, or a rectangle which has 2 fields. And we can define a method in this area, like this impulse shape block. You can define a method. It has this little self parameter, which sort of just says, I take. You want me to speak into the microphone? Ah, there we go. That's much better. So the self parameter is for it's to indicate that this isn't just a plain function. It's also a method. In Dart, you might be used to this sort of being implicitly exists in every. You can always use this in any method unless it's static. But in Rust, if you don't have this self, then it's a static function. And then here we can create a circle. We can get its error and print it. So if you're using Rust in Dart or Flutter, you have to go through this thing called FFI, which is a foreign function interface. And effectively, all FFI is the ability to call functions written in one language from another language. So here we have like some Dart code calling this Rust double function. But it's a bit more complicated than that. You can't just call the function. There's some steps you have to go through. And so reasons why you might want to do this. For us at Ditto, a really big thing is code reuse. So we support 9 languages, and we do not want to have to build our entire product 9 times in 9 different languages. That's not good for various reasons. It's expensive. Also, you end up with different bugs on different platforms, different feature support. You don't want it. The other big one is performance. I did a quick mock-up of some core piece of logic inside Ditto in Dart before this talk, and got roughly 10 times faster performance with Rust. Benchmarks are hard. It's not a blanket statement, but Rust is extremely fast. Sometimes you'll have libraries that just don't exist in Dart. Like maybe you've got a strange format you need to parse, and there's only, you can only find one written in Rust, or you're given vendored binaries. You work with a vendor who only provides a C header and a blob. Then you have to use FFI. It does come with some risks though. So the really obvious one is platform support. You can't rely on Dart to give you platform support anymore. If you want to support Windows, you have to build your binaries for Windows. You have to link them. You have to figure out the Windows build process. A new platform gets announced, that's on you. If you just write your library in Dart, the Dart team will figure that out for you. You can not worry about it. The other thing is that the crashes tend to be nastier. So in Dart, you'll get an exception thrown, it'll bubble up, you'll get a nice error message, it'll give you a stack trace. That's not always true with FFI. You can cause undefined behavior, you can just crash your process outright, you get no logs, you just get process terminated in your terminal. It's usually, it can be nastier, but there's techniques to get around that, which I'll go into. So I've spoken a little bit about Ditto. I have a quick sales pitch that you can tell the slides are made by the marketing team, not me. It's a little bit like Firebase, but peer-to-peer. So you might have heard people explain it at the booth, but basically it's a NoSQL database that you can embed in your app. You can query it locally, and if you enable Bluetooth or peer-to-peer Wi-Fi, it will form a mesh with nearby devices and synchronize between them. So you can insert into users on one device, and if another device is interested in the user's collection, it will grab that data from the first device, synchronize them. If you want to use the cloud, you can. If you don't have to. Peers there's no sort of central peer. They just sort of form this distributed mesh. It's powered by these things called CRDTs, which are conflict-free replicated data types. If you ever use Google Docs or Google Slides, for that matter. They're sort of a core data structure that allows collaborative editing. So they can take any two sets of changes and merge them together without conflicts, hence the conflict-free. They do have eventual consistency, which is a little bit of a downside, but for what you're getting, I think it's worth it. And we have our little query language. We call it DQL. It's a Ditto query language. It looks very familiar if you've ever used SQL. It's by design. The underlying model is much closer to a NoSQL database though. So we have our Rainbow connection, which is all of our different transports. So peer-to-peer Wi-Fi, USB, cellular, LAN, Bluetooth Low Energy, and sort of more traditional Wi-Fi where you're connecting to an access point. There should also be cloud on this slide, but and we have multi-hop as well. So you can be on a device and it connects via Bluetooth to another device, which connects to through peer-to-peer Wi-Fi to a point of sale system, which goes to a server, which goes to the internet and goes to your backend API through Kafka. Or it's quite a flexible system. One thing that people often worry about when they come across Rust is that it's a low-level language, meaning you're dealing with pointers, you're dealing with references. You have to decide, is this variable going on the heap? Is it going on the stack? Sometimes you don't have a choice. You have to work around that. I say manual memory management. It's a little bit of a lie. It does clean things up for you semi-automatically. But a big concern people have when they're thinking, especially if they've used C a lot or C++, is like, do I really care about this extra performance? Is it that useful? Is it worth the risk? People may have heard of undefined behavior. It's a big thing in C and C and Rust, but all these languages have undefined behavior. But the idea is basically there are some things that if you do them, the compiler is allowed to emit whatever assembly it wants. It can emit assembly that does nothing. It can emit assembly that writes the wrong variable to some place in memory. It can do effectively anything, and you've given up your right to complain because you've invoked undefined behavior. If you're lucky, you'll get a crash. If you're not lucky, it will just do the wrong thing. If you're really unlucky, it will do the right thing in CI and the wrong thing in production because your customer is using an ARM machine and you've never tested it on ARM servers in CI on a Wednesday. And the other really nasty thing about them is they tend to cause security vulnerabilities. So Microsoft published a report a few years ago where they did a review of all the security vulnerabilities they had. They found that 70% of them came from this kind of mistake. That's quite a lot of security vulnerabilities if you've ever used Windows. There's a few. So this seems really bad. Why would you want to expose yourself to it? Well, Rust tries very, very hard to make sure that you don't. So here we've got, on the top, we've got some Rust. On the bottom, we've got C. And they're both doing the same thing. They're functions that they receive a pointer to an integer, they dereference that integer, they double it, and they return a pointer to the doubled value. Some of you may be seeing the error here already. This is unsound code. This will likely crash your program, or worse, if you use this. And the reason why is because this y is stored in the stack frame for this function, but as soon as this function returns, that stack frame's getting destroyed. You're pointing to like invalid memory. It's a dangling pointer. If you try to read that pointer, bad things will happen. But the Rust side doesn't compile. The compiler can see that you're referencing data that is tied to the lifetime of this function, and so when the function returns, it says, you're trying to reference invalid data. It catches it. And this is a theme throughout most of Rust is if it can cause undefined behavior and you're not using the unsafe keyword, then it won't compile. And this is really, really nice for giving you that kind of, making you not worry so much about the sort of terrible things that can happen traditionally with FFI. So if you actually want to use it from Dart, there's a couple of things you have to do. On Rust, you've got this no mangle, this extern C, which sort of says, don't rename my function and pretend to be C, because Dart only really speaks. Most languages only communicate through the standard like sort of layout that C uses. We get this dynamic library class from Dart, and we can use that to look up a function by its name. Because we've put no mangle here, our compiler's not going to rename the function, and this will work. And you can call the function, and it works. You've doubled a function. It's not particularly interesting, but you can imagine you can have some game of life simulator or something very complicated here. It doesn't matter that much. So in Ditto, we have our cargo.toml file, which is a bit like pubspec.yaml, spiritually equivalent. And we say this crate type equals static lib. And what this will do is it will say that it will tell Rust that when we build our project, we don't want like a Rust binary or anything like that. We just want a library that can be slotted into another application. And then we use some CMake magic. We sort of copy it into this. Here we're doing android/lib for our Flutter plugin. And we just say, look, include this, make all of the functions in this library available to Dart. And so we don't write the bindings by hand, because there's like 500 functions, and I would absolutely make a mistake doing that. And mistakes here are dangerous. If you pass the wrong type, there's no type checking across languages. It will just call it with whatever it thinks is in that piece of memory, and you'll likely break. So instead, we use this tool that's published by the Dart team called FFI-gen, which sort of consumes this header file, which is like the sort of this definition of all your functions and types and stuff. And it generates this big file that contains all the correct types. It's a huge file. You never really inspect it, but it does the right thing. And then we make these classes like ditto query result, which really just contains a pointer to some Rust structure. Our ditto class is just a pointer. It's just a thin wrap around a pointer to a structure. And it doesn't work. Failed to look up symbol ditto get SDK version. What's going on here? Well, if we go back to the slide on how we looked up a function, if you notice something, this is all runtime code. This is all happening dynamically. This Rust double string, it happens to be a string literal, but it could be the return type of a function. We don't know. The compiler doesn't really know either. And so from the compiler's point of view, we've just linked in all of these huge functions. The ditto binary is like 30 megabytes. So we've got 30 megabytes of code. And as far as the compiler's aware, it's never being used. So being a very clever compiler, it decides, well, that's all dead code. I'm going to eliminate all of it. So it eliminates all of the functions we've just pulled in, which is annoying. So the fix is quite simple. We just trick the linker into thinking that we're using it. So we have this function that just gets every ditto FFI function that we ever use and assigns it to this pointer. And because the pointer's marked volatile, the compiler's not free to eliminate those like assigns. And for all it knows, they're very important. So it keeps them, and this works for now until the linker gets smarter, I guess. There is hope for the future though, because of this. It's an experimental feature that's coming to Dart, or I think it's coming to Dart. I'm not sure. Where you can sort of tag an external function and say, look, this is the name of the function, this is the signature. Can we, do this at compile time? And hopefully this sort of dead code information can be propagated throughout the thing. So if we have a customer of our SDK who's only using, they're only using 2 functions, that information can go through the linker into, like, it understands that most of that 30 megabytes is unneeded, and it can get rid of a lot of it. It isn't usable yet, but we're hoping. So that's how we call Rust from Dart. But a really key part of our SDK is how we go the other way, calling Dart from Rust. And here we've got equivalent Dart and Rust. It's just we've got a Dart callback and we've got a Rust callback. There, you've got these horizontal, vertical bars. If you ever programmed in Ruby, it's the same syntax. And then we take a function as an argument and call it. This comes up in the real world with logging. So every time the Rust core receives some important event, it will call this log function. And an important part of our SDK is we want our users to be able to supply a logging function. So maybe it's going off to Sentry, or it's going off to their log collecting system, or it's just going to the console. It's really up to them. So the question is, what goes in this convert function? How do we take, Rust is expecting a function pointer. It's expecting 8 bytes pointing to a location in memory with some machine code. How do we get that from Dart, with the correct function signature? So Dart provides 3 methods of doing this. All of them have some drawbacks, but we'll go through them. So pointer.from function is kind of the most basic one. And what it's doing is it only supports static or top level functions. So there's no closures, no sort of state in your function, which is kind of a non-starter for us because we need people to be able to call things with state. That's really important. So then there are these 2 native callable ones. Isolate local is interesting. It allows any function with any signature, but it's not thread safe. The pointer that you get can only be called from the thread that it was created on, which shouldn't be a problem, except that our Rust core uses a work stealing scheduler. So that function pointer maybe is going to get moved onto a different thread. If one CPU core is really busy and another one's fine, it might just hop over to the other one, and now you've got undefined behavior again, and everyone's unhappy. So the final one is native callable.listener, which I believe is implemented just as a wrapper around isolate local, which will sort of just send your payload to the correct isolate whenever you call it. And that sort of solves our issue. You can only return void, which is slightly annoying, but it's solvable with Dart stuff. So it should be simple. We have our Rust code up here, which is it's just receiving an event, processing it a bit. So it's doing things like adding null termination, some Unicode stuff, and it's calling the callback. And now the callback's finished, so of course we're done with the string, so we can drop the string, releasing the memory back to the OS. I see someone shaking their head. Someone knows. And here on the Dart side, we're just receiving a pointer to a array of bytes containing a null pointer at some point. We're casting it to UTF-8, turning it into a Dart string, and just printing it. Unfortunately, this also doesn't work. We get strange crashes, missing logs. What's happening? So this is what we expected was happening. We expected we'd have Rust receiving a logging event, and it goes into some global variable, finds that Dart callback, and marshals the arguments, calls the function. Then Dart takes the data, copies it into Dart VM managed memory, and then the callback returns. We free the string. Everyone's happy. Unfortunately, this is not what happens. What actually happens is Rust gets the event and calls the callback, and Dart receives the callback and immediately returns and schedules the callback for some point in the future. But it's not. It's just given a pointer. It's just given a location in memory, and there's nothing that guarantees that that location in memory is going to contain what we think it contains at some point in the future. We don't have control over when Dart schedules that. So Rust then immediately frees the string. Deterministic sort of resource releasing is a big feature of Rust. So it always frees the string immediately after that call returns. Dart then schedules the callback for some point in the future. And when it runs, who knows what's in that memory? It's a pointer that's been freed. This is a use after free. It's classic undefined behavior, and yeah, it blows up. The solution is quite simple. We just, in Rust terminology, we'd say we're passing ownership of the string into Dart. We're saying the responsibility for freeing this bit of memory now belongs to Dart. It's your job. You need to call free. You have to call Rust's free, though. You can't call Dart's free, because if you free something from Dart that was allocated in Rust, that's also undefined behavior. So, be careful there. And yeah, so all we do is we expose another function called like ditto string free, something like that, and we call that at the end of the log. And that brings us on to the final sort of big problem we encountered, which was to do with JNI. So JNI it's kind of like Java's flavor of FFI. It's a way for you to write C code or really code in any language that can communicate with C and have it interact with Java. So if you've ever called any Java code from Dart using the JNI package, that's what it's doing. It's a fairly simple protocol. It's basically just you get this big struct that has 100 function pointers in it, and they all do it's like get class by name or look up like get version, these kinds of things. So the reason this is important for us is because at Ditto, we're building peer-to-peer meshes. We need to be able to turn Bluetooth on, turn Bluetooth off when we want to. It's something we manage rather than something that the user of the SDK manages. So that requires, because Android, a lot of the system calls are sort of Java-based, we need access to this JNI environment to be able to call any of them. So the rough idea is we take a pointer, we get the pointer from Dart, we pass it into Rust, Rust stores it in a global somewhere, and then the Rust core can call these functions whenever it wants to. So here's a little bit of the code doing it. This is using the Rust JNI library. We have this get JNI end, which just loads it from a global pointer, a global variable. And we sort of look up the class by its name. We look up an object. There's lots of stuff that wouldn't fit on a slide. Just lots of big strings. But there's some ceremony here, but it's fairly straightforward. You're just loading an object, loading a method, calling a method. It is an unsafe function, which is a little bit troubling. The reason for this is it's up to us to decide to make sure that we have the right types, and we're calling a function with the right number of arguments. This at the bottom, you can see the little reference square brackets. Which line is that? Line 18. These are the arguments. There's no compile time check stopping you from providing 100 arguments to this function. And that's why it needs to be unsafe. If you pass too many arguments, bad stuff will happen. If you pass too few, bad stuff will happen. If you pass an argument that's a string that's meant to be an int, bad stuff will happen. So we tried it. We did it the obvious way, and it segfaulted on a null pointer deref, which is strange, because all we're doing is we're taking this pointer from Dart's JNI package, we're passing it to Rust, using Rust's JNI package to look up a class. It could say like class not found. That's something I would have expected, but it didn't. It segfaulted. So what's going wrong here? Well, this is a very, very small snippet of the official JNI header file. So this is the file that defines all of the types, just like we have with Ditto, defines all of the types, all of the function parameters, everything for a call to a JNI function. And here we have the one that's used by Dart's JNI package. Now, if you couldn't see the difference between them, I don't blame you, because I stared at this for like 3 weeks and I couldn't see the difference between them either. Sorry. No problem. It's quite tricky. If you put them next to each other, though, it becomes a bit more obvious. It's very hard to see when you've been staring at pointers for weeks. But there's this extra parameter on the sort of official one that we got from Oracle. There's this extra like JNI-env pointer. And if you think about it, this is just this in an object-oriented language. This is just a pointer to the object that's calling it, right? It's effectively just a sort of hidden function parameter that's on every method. The Dart one doesn't have it. And there was code in the repo to remove it from the official one that I commented out. And I don't know why it's that. I'm sure there's a good reason. I don't know what it is. Okay, so we made our fork, we patched it, and it works, right? Well, little foreshadowing, but it does not work. So at this point, it fails to find the classes. And this is where I really just have no idea. The Android specialist on my team has no idea. He found an Android history book that referenced this thing called a Zygote class loader. Like Zygote, like a tiny baby. Like I don't know. He's going into history books. I've never had to open a history book for my job before. This is not what I signed up for. If you know why, please get in touch. We would love you. I've been given a company credit card to buy you a coffee with. I would love to know the answer to this. Now, the real solution that we have is it's not actually required that we call like enable Bluetooth and whatever from Rust. This isn't. It's convenient. It matches our other SDKs, so we have the same code path for all of them. But it's not working. We don't know why, so we can work around it. So what we are currently working on is a solution to just instead of passing this JNI pointer into Rust, what we do is we create the just plain callbacks in Dart that find this Bluetooth manager class and call it from Dart, because in Dart we can see the classes, and then we take the same pointer and send it to Rust, and we can't see the classes. It's very confusing, but we can see them from Dart, which means we can pass function pointers that can see it into Rust, we think. And if we can pass that into Rust, then instead of Rust invoking JNI directly, it can just invoke these callbacks that we pass in, and it's a bit messier. It's out of sync with our other SDKs, but we think it will work. So yeah, that's all I had. Any questions?